Let's now take a look at the thread semantics. So let's extend the abstract machine with the new concept of thread. The way we do it is that we add a new semantic stack for each thread that we create. So the instruction thread end will create a new semantic stack, and all of these will share the same memory. In the overall execution, there is still one sequence of execution states, and threads take turns executing instructions. So instead of having one semantic stack in the execution state, we now have a multi-set of semantic stacks. And that means we have a set of them. We can have more than one, but the elements might be the same. Two semantic stacks might, by some chance, have exactly the same instructions in them. So it's a multi-set and not a set. And then each execution step then takes this multi-set and the memory and does one step. This is called interleaving semantics, as the execution of all the threads is interleaved to form the one global execution. So let's take a look now at the rule that the thread instruction does. So here we have a semantic stack with a thread instruction on top. It's about to create a new thread. And when it executes, applying the rule for threads, it will create a new semantic stack with the instruction S, which was in the thread, and then there will be the original semantic stack with the instructions below the thread will remain. So we have now two semantic stacks. Let me say a few words about interleaving semantics. And the question is, what happens when activities execute at the same time? We can imagine that all the threads are executing in parallel. Each has its own processor, and they're accessing the same memory. But we have to be very careful here. What happens when two threads simultaneously operate on the same memory word? They're stepping on each other's toes. If we use interleaving semantics, the threads are sharing the same processor and taking turns. This problem is avoided. So interleaving semantics is much simpler to reason about than truly concurrent semantics, where the threads are allowed to step on each other's toes and operate on the same memory word at the same instant. Now, usually we don't need truly concurrent semantics, because even in the case when the threads would step on each other's toes, the hardware of this processor will make sure it doesn't happen. For example, in a multi-core processor, we can have several cores. Each core is a processor. Each core is running instructions. If they try to operate on the same memory word at the same time, there is what's called a cache coherence protocol, and there is a well-defined behavior. There's going to be no fighting going on between the threads. Some well-defined interleaving behavior will happen. So interleaving semantics, in fact, is very reasonable, and the hardware does some effort to maintain this semantics. Now let's talk a little bit about ordering of the execution states, and in fact, this is the source of non-determinism. So in a sequential program, execution states are in a total order. That means when I do one step and another step, one of them is before the other. It's defined by the program. It must be like this. Okay? In concurrent programming, this is true in the same thread. Execution states of the same thread are in a total order because the instructions of the thread have a well-defined execution order. But this is no longer true for the whole program with more than one thread. These are in a partial order. It means if two threads are executing, then between this thread and this thread, there's no order defined. So if I take any two execution states and see what they're doing, there may not be an order defined if they're working on separate threads. So in a concurrent program, when we actually run the program, we have one execution. Now, many executions, actual running executions, will be compatible with the partial order defined by the threads. And in fact, one of them will actually take place when the system actually runs. Which one? Well, we don't know. The scheduler is going to pick it, is going to choose it. That's a non-determinism. So here's a picture for a sequential program. The execution states are in a total order. So here we have total order. Every execution state is well placed before every other one. Okay? Now let's take a look at concurrent program. So here we have 3 threads, T1, T2, T3. Each thread inside itself has a total order, but in between the threads there is no order unless there might be some synchronization. So for example, we have a data flow variable x which is bound in T2 and which is used in T3. So this will impose a constraint on the order. That means some state here has to happen after the other state there. So given the total order within each thread and the constraints between the threads because of the synchronization, this gives an overall partial order, and this partial order is compatible with many real executions. Okay, many executions are compatible with the partial order. The scheduler will pick one of them. How does it pick? Well, it has its rules. It's defined in a certain way, but it's not the programmer, it's the scheduler that picks one of them, and this choice is the origin of non-determinism.